So the first question is, let T be the set of all triangles in a plane. R is a relation in T given by R is equal to T1 comma T2 such that T1 is congruent to T2. Show that R is an equivalence relation. So here it is means basically you have to show that this is an equivalence relation. That is very easy. As we have discussed just before, you have to check for is it reflexive, symmetric, transitive or not. Correct? Okay. So now this relation is defined on set of this, let T be a set of all triangles in a plane. R is a relation defined in T. Okay. So what does this T contain? All triangles in a plane. You take in one plane. Okay. Let us say you take this plane. You have different triangles. You have different lengths, different angles, equilateral triangles, scalene triangles, isosceles triangles, different types of triangles, acute angle triangles, obtuse angle triangles, right angle triangles, everything. Okay, all different sizes, everything is there in your set T because T contains all triangles in a plane. In a plane, how many ever triangles you can draw, whatever all different triangles you can draw, all of them are there in our T. Okay, nothing to this is a very simple question. Okay, T is containing all these triangles. Next, with R a relation in T. So R is defined on T. So R is a relation which is a subset of T cross T. Given by R is equal to T1 comma T2 is an ordered pair if T1 is congruent to T2. If the first triangle is congruent to the second triangle, then that ordered pair will be there in our relation. Clear? Okay, fine, right. So we have to show that this is an equivalence relation. No problem. First, let us start with reflexive. Is it reflexive or not? When will it be reflexive? It will be reflexive if every triangle in this set T is mapped to the same triangle. Okay, let us say for example, okay, there is one triangle here. Can I map it to the same triangle? Of course, this triangle, if it is here, it will be here also because it is the same set. So now, what is the condition? First triangle should be congruent to the second triangle. This triangle, is it congruent to the same triangle? Is it true or not? See, one triangle is congruent to itself. What is the meaning of congruency? Congruency means something like this. Let us say you take your palm. Okay, you take your palm. You are putting it on this palm. Then it is exactly fitting. This is what is called congruency. Congruency means they are same, just exactly same. Okay, so then you call two things congruent. That's all. So therefore, here every triangle is congruent to itself because every triangle is same like itself, right? Okay. So therefore, it will be reflexive because what is reflexive? Every element in this set should be mapped to the same element. So therefore, you take any triangle, it will be congruent to itself. So therefore, that is mapped to the same triangle, right? So therefore, you understood, right? So therefore, this will be a reflexive relation. Simple. Okay. So that's all. This is reflexive. Okay. What is the reason? R means reflexive. Okay. So what is the reason? Every triangle is congruent to itself. Every triangle is congruent to itself. Okay. This is for reflexive relation. Now, what about symmetric relation? Is it symmetric? Okay. Now, what is the condition for symmetric? If you have, let us say for example, this ordered pair itself, T1 comma T2. This is a ordered pair which is belonging to our relation. Means the first triangle is congruent to the second triangle. Only then this ordered pair will belong to our relation. Correct? Okay. So this ordered pair is belonging to our relation. Okay. If this is happening, then T2 comma T1 also should belong to our relation. That is what we have to check, right? Okay. If there is an ordered pair, then its reverse also should be there. So if T1 is congruent to T2, means if you are putting T1 on T2, it is exactly fitting. No problem. If you are putting T2 on T1, it will anyway fit, right? So therefore, if T1 is congruent to T2, then T2 is also congruent to T1. So therefore, this will be a symmetric relation. Now, what about transitive? Transitive means, will it be transitive? You only tell me. Okay. So T1 comma T2 belongs to R and T2 comma T3 belongs to R. Then T1 comma T3 should belong to R. What is the condition? If T1 comma T2 is belonging to our relation, then T1 is congruent to T2. T2 comma T3 is also belonging to our relation, means T2 is congruent to T3. Means T1 is exactly like T2. T2 is exactly like T3. Means T1 will be exactly like T3 only. So therefore, this will be transitive, isn't it? Right? So therefore, so that is what we have to write in boards format. That's all. Okay. So such a simple question, just we are writing in boards format. You have understood why it is reflexive, symmetric and transitive, because we have to show that. Okay. In show that questions anyway, you know the answer. So you can build up to that in some way, but you have to know why you are writing like that also. So let us come to the solution. Okay. First, let us write for reflexive. Okay. So R is a reflexive relation. R is a reflexive relation. Okay. Just a minute. R is a reflexive relation on T, on set of T. Okay. On T, because as every triangle is congruent to itself. Every triangle is congruent to itself. Okay. Therefore, that's it. So we told that it is reflexive, and we have given the reason also why it will be reflexive. Because every triangle is congruent to itself. So therefore, R is a reflection on set T. Okay. So first thing is completed. Next, let us come to symmetry. Okay. If T1 comma T2 belongs to R, implies T1 is congruent to T2. Right? Okay. Now from this itself we can write this also, implies T2 is congruent to T1. If T1 is congruent to T2, T1 will be mapped to T2 under the relation. So T1 comma T2 will belong to our relation. If T2 is congruent to T1, then T2 will be mapped to T1 under the relation. So implies T2 comma T1 belongs to R. Therefore, R is symmetric relation. Okay, simple, fine. So we have proved that this is symmetric also. For transitive, again the same procedure. Okay, so let us write that as well. So if T1 comma T2 belongs to R and T2 comma T3 also belongs to R. Just before we have written this is a symmetric relation. Just after that you write on T, on set of T. Okay. So R is a symmetric relation on T. That will be on T, you have to attach there. So if T1 comma T2 belongs to R and T2 comma T3 belongs to R, then implies, what is the meaning of this? Implies T1 is congruent to T2 and T2 is congruent to T3. Congruent to T3. Now if T1 is congruent to T2 and T2 is congruent to T3, implies T1 is congruent to T3. Implies T1 comma T3 belongs to our relation. So that's it. Therefore, R is R. Okay, so if you want, you can put it like this. Otherwise, it is not needed also. These apostrophes. R is a transitive relation. Transitive relation on T. Okay, so therefore, we have shown that R is reflexive relation, R is symmetric relation, R is transitive relation. So therefore, that's it. So implies, so finally, after this, implies R is an equivalence relation. Equivalence relation. So that is what we had to show, and we have shown. Whenever you see equivalence relation, your means the first or the line of thinking should be you have to check for reflexive, symmetric and transitive. Show that means you have to show that it is reflexive, it is symmetric and transitive also. Simple. Okay. So let us take the next question. Very simple question, right? Okay. Show that R in set 1, 2, 3 given by R is equal to 1, 1, 2, 2, 3, 3, 1, 2, 2, 3 is reflexive but neither symmetric nor transitive. So we are given a relation and we are given a set. So let us say our set is set A. Okay. Because here there is no name given for that set, I am giving a name that is set A. Okay. So R is defined on this set A and R is having these ordered pairs 1, 1, 2, 2, 3, 3 and 1, 2 and 2, 3. Okay. So now is this reflexive? Just by seeing I can say this is reflexive because every element of A is mapped to the same element. 1, 1 is there, 2, 2 is there, 3, 3 is also there. So therefore this is reflexive. Show that this is a reflexive. Show that this relation is reflexive. Okay. As 1, 1 belongs to R. Okay. 2, 2 belongs to R and 3, 3 belongs to R. So after this closing line, implies R is a reflexive relation. Okay, R is a reflexive relation on the given set. On the given set. So that's it. R is a reflexive relation. Next, is it symmetric? How do we check for it? This we know very clearly. You take ordered pair. You take one ordered pair 1, 1. Is reverse there? Yes. So this procedure is for your checking. Okay. You need not write tick marks here. Okay. In boards. So 1, 1 you are checking. So you got a tick mark. Okay. Next, because reverse is also there. 2, 2 reverse is also there. You got a tick mark on this also. 3, 3 on this also you got a tick mark. 1, 2 is there. You have taken. The reverse 2, 1 is it there? No. So therefore this is not symmetric. Why? Because you have checked for it and you are getting one cross mark. Even if you get one cross mark, you can stop and then you can write the reason. So R is not a symmetric relation as 1, 2 belongs to R but 2, 1 does not belong to R. Okay, is not a symmetric relation on the given set. Okay, sometimes it is better to write this one, especially for boards. Okay, otherwise for competitive exams, however you do, if you get the correct answer, that is more than sufficient. So R is not a symmetric relation on the given set as 1, 2 belongs to R but 2, 1 does not belong to R. So when you are proving, then you are showing, why this is reflexive. When you are disproving, then you can give one example where it is not happening. That is sufficient. Okay. So here we have shown that this is not symmetric relation. Next one will be transitive. This checking will be the same procedure that as we have, studied just before. 3, 3, 1, 2 and 2, 3. So what is the procedure? You take one ordered pair. So take the second coordinate 1. Is there any ordered pair starting with 1? Yes. So 1, 2 is it there? Yes, it is there, right? So therefore means 1, 1, 2 is there. Is there any other ordered pair starting with 1? No. So therefore on 1, 1 you got a tick mark. Okay, checking for this ordered pair is completed. Next, take this ordered pair. Is there any other ordered pair starting with 2? Yes. This is the only one. So 2, 3 is it there? 2, 3 is there. So therefore checking for this ordered pair is completed as we have checked with all the ordered pairs which are starting with 2 other than this one. Okay, fine. Next 3, 3. Is there any ordered pair starting with 3? No. Other than this one, there is no other ordered pair starting with 3. So therefore no checking is needed. For this also we got a tick mark. Next 1, 2. Is there any ordered pair starting with 2? Yes, here we have. So 1, 2 should be there. It is there. Next, any other ordered pair starting with 2? Yes, this one. So 1, 3 should be there. Is it there? No. So that's it. You need not check further. You got a cross mark. So therefore, for 1, 2, we got a cross mark. So why is this? R is not a transitive relation. R is not a transitive relation on the given set. Okay, on the given set. On the given set, as 1, 2 belongs to R and 2, 3 belongs to R, but 1, 3 does not belong to R. So that's it. You have shown that this is reflexive, this is not symmetric, and this is not transitive. In all of them, you have given the reason. That's it. Okay, clear? So let us take the next question. Show that the relation R defined in set Z given by R is equal to A comma B such that 2 divides A minus B is an equivalence relation. So let me pause for a moment. You try, write it in your book. You know very well how to check for equivalence relation and then come back and see for the solution. Okay, so now I am sure that you would have proved that this is an equivalence relation. If you had any problem or any doubt, let us, start doing the solution. So here we have a relation which is defined on set of integers given by R is equal to A comma B and 2 divides A minus B is the condition. So is an equivalence relation. When do you call this as an equivalence relation? When it is reflexive, symmetric, as well as transitive. So when is it reflexive? When every element of set Z is mapped to the same element, or in other words, A comma A should belong to our relation for all A belonging to set of integers. For every element in set of integers, it has to be mapped to the same element. These ordered pairs should be there in our relation, right? Okay. So here, if this ordered pair should belong to our relation, the condition is the first coordinate minus the second coordinate should be divisible by 2, right? Okay. So now, first coordinate minus the second coordinate, this should be divisible by 2. This is equal to 0. Is 0 divisible by 2? Yes. So therefore, A comma A will belong to our relation. That's all. Divisible means nothing. See, if you have, let us say 10, you are dividing by 5. When you do the division without any points, you should get one integer. That's all. So 5 ones are, 5 twos are. So therefore, this is what you call, divisible. A minus B, 2 divides A minus B. So divisible. So 10 is divisible by 5. That is what is the meaning. So here is 0 divisible by 2. 2 into 0 is 0 only. So therefore 2, if you are multiplying it with 0. So anyway, you all know this. So therefore, let us go ahead. So therefore, A minus A belongs to A minus A is equal to 0. And 0 is divisible by 2. Is divisible by 2. So if it is divisible by 2, then this ordered pair can be in our relation. That is the only condition we have. First coordinate minus second coordinate should be divisible by 2, which is happening. So here, this is a reflexive relation because A comma A belongs to R for every element belonging to set Z. That's it. So reflexive is completed. How about symmetric? Okay. So symmetric means we have to start like this. You know very well now, right? If you don't know, understand this. This is the way you have to start. How? You take any ordered pair A comma A. See if it is belonging to our relation. Based on the condition, you will have the rule. Means here A minus A should be 0. Sorry, A minus A should be divisible by 2. So therefore, based on the rule, you will be able to say if this is belonging to our relation or not. So that is the procedure for reflexive. Okay. Next, this will be very helpful in CET as well as JEE also. This method, okay, means not the way of writing, but the way of checking. Next, for symmetric, how should you check? If A comma B belongs to R, okay, then from here you have to prove that B comma A can also belong to R. If you can prove, then that will be reflexive, that will be symmetric, otherwise it will not be symmetric. Now, So from here, because this is belonging to our relation, you can write one, based on this condition, you can write one condition here. 2 divides a minus b. So a minus b is divisible by 2. Okay, a minus b is divisible by 2. So if a minus b is divisible by 2, from here, can I do something and finally get to proving b comma a belongs to R? How can you prove that this is belonging to R? Implies b minus a should be divisible by 2. So by doing something, can you come to this place where b minus a is divisible by 2? Okay. So what is the only difference here? You have a minus b, there you have b minus a. So if you are taking one minus sign common, you have b minus a, just one minus is there outside. Okay. So like this only. Let us say, for example, if I say 10 is divisible by 2, correct? Okay. So is minus 10 divisible by 2? That is also correct. If 10 is divisible by 2, because of minus, nothing will change, right? Isn't it? Minus means minus 1. So if the number is divisible by 2, then minus of that number will also be divisible by 2. So in a way, what I am saying is you take any number. Okay, if this is divisible by 2, then minus of this means that will be 10. That will also be divisible by 2. So on the whole, you understood by changing the sign. If the number is divisible by 2, then it will be divisible by 2, even if you put plus sign or minus sign. Simple, right? Okay. So so that's also implies b minus a is divisible by 2. So therefore, b comma a belongs to R, right? Okay. So next will be if a comma b belongs to R and b comma c belongs to R. So now we are checking for transitive. We know this is the method, as I told you. This is the same method. Whenever you are checking for reflexive, symmetric, or transitive, a comma a belongs to R or not, a comma b belongs to R, then seeing for b comma a belongs to R or not. And for transitive, if a comma b belongs to R and b comma c belongs to R, then a comma c, does it belong to R or not? This is the same procedure, just the condition will be different and the equations will be different. That's all. So if this is happening, means a minus b is divisible by 2. Okay, divisible by 2. And if this is happening, b minus c is also divisible by 2. So now from here, what we should prove for it to be transitive, a comma c should belong to R. Means a minus c should be divisible by 2. From this information, first equation, there is no equation here, first statement, second statement. With these two statements, can you prove that this is true? Okay, so let us get into little mathematics. It will be very helpful to see in that manner. Let us start with this symmetric itself. A minus b is divisible by 2 means a minus b is 2 times some integer, where k1 belongs to integers. So if you are taking minus common here, it will be b minus a, which will be, obviously, we are writing the same equation. Right hand side will be 2k1. Now you take minus here. So b minus a is equal to minus 2k1. The same thing I can write it as 2 into minus k1. Okay, no problem. Till here everything is fine. Now I wanted to have b minus a is divisible by 2. Almost I have it, right? 2 into something. Now this should be integer. Just before we have discussed, 10 is divisible by 2. Means when you divide 10 with 2, you should get an integer. So basically what we are saying, so therefore, let us say this is some integer, here it is 5. So 10 can be written as 2 into some integer. Same thing, if I am saying if you divide, you should get some integer, you can write this as 2 into some integer, right? So therefore, here. So if a minus b is divisible by 2, then a minus b can be written as 2 times some integer. Okay. Now what did I get? B minus a is equal to 2 times minus k1. K1 is an integer. If k1 is integer, minus k1 is also integer. So therefore, we got 2 times integer. So if we got 2 times integer, that means b minus a is divisible by 2 only. So if b minus a is divisible by 2, then b comma a belongs to R. So this is the mathematical way of showing that if a comma b belongs to R, then b comma a also belongs to R. Let us do the same thing here also. So here, this is saying that this is 2 times some integer. some integer, okay, where k1 is some integer. In the same way, b comma c, b minus c, okay. So b minus c is divisible by 2 means b minus c is 2 times some integer, okay, where k2 is some integer. Now finally, what should I prove, or what am I looking for? A minus c should be divisible by 2, means a minus c should be 2 times some integer. Okay, so given these two informations, can I prove that that is happening? Correct? That is what we are saying. If this is belonging to R and this is belonging to R, can I say that this is belonging to R? So if this is belonging to R, this is the condition. If this is belonging to R, this is the condition. From these two things, can I say that this is happening? Okay, what is the extra thing here? Means A is there, C is there. I don't want B. So therefore, let us add these two, because by doing which B will get cancelled. So when you add these two, what will happen? A minus B, let me write it here, A minus B and plus B minus C. And on the right hand side, you will have 2 into K1 plus K2. 2 into K1 plus K2. Okay. Left hand side is very good. Means the way we want it, it is there. A minus C. So A minus C is equal to 2 into K1 plus K2. So I am sure, all of you would have seen by now. It is already there. See, K1 is an integer, K2 is an integer. Sum of two integers will be an integer. So therefore, A minus C is 2 times integer. Means A minus C is divisible by 2. Means A comma C belongs to R. So therefore, it is transitive. Understood? Right? Okay. So therefore, let us write the same thing in the way that, you have to write in boards, not in a, very rough type of way, in a fair way. So A comma A. So what should we, so A comma A belongs to R as A minus A is equal to 0 and 0 is divisible by 2. Divisible by 2. So therefore, what did we say? A comma A belongs to R for all A belonging to the set of integers. For every element in set of integers, it is mapped to the same element. Therefore, R is reflexive relation. R is reflexive relation on Z. Clear? So reflexive is completed. Next, what do we need to do for symmetric? Same method. Whichever is the question, say if A comma B belongs to R implies A minus B is divisible by 2. Divisible by 2. And we know very well how to write this mathematically. Implies A minus B is equal to 2 times K1, where K1 is a integer. Okay, so from here I can write minus of B minus A is equal to 2 times K1. B minus A is equal to, send the minus on to that side. So I will have minus 2K1. I can write it like this. So therefore, implies B minus A is equal to 2 times integer. Okay, here reason. Since K1 belongs to Z implies minus K1 belongs to Z. Simple. Okay, so if you write like this, it is therefore. If you write like this, it means since. This is therefore. This is since. Since K1 belongs to Z implies minus K1 belongs to Z. So therefore, this is an integer. So implies, what did we say? B minus A belongs to R. So therefore, if A comma B belongs to R, implies, this is implies B comma A belongs to R, not B minus A. So this is comma. So implies R is symmetric relation on set of integers. Simple. Okay. So now let us take the next one, and that is for proving that this is transitive. If A comma B belongs to R and B comma C belongs to R, till here it is fine, right? If these two are belonging to R, then we have to prove A comma C belongs to R. Okay. So this will belong to R implies A minus B is 2 times some integer belonging to Z. In the same way, B minus C is also 2 times some integer. This is, let us say, first. This is, let us say, second. So first equation plus second equation will be plus B minus C is equal to 2 into K1 plus K2. Implies here B is getting cancelled, and therefore we have A minus C is equal to 2 into some integer. What is the reason? Since addition of two integers is an integer. Addition of two, okay, let me write it here, integers is an integer. So here the bracket is closing. So A minus C is 2 times some integer. So that's it. After that it is very simple. So implies A comma C belongs to our relation. So that's it. So therefore R is transitive relation. Transitive relation on set of integers. So therefore R is reflexive relation. Sorry, R is equivalence relation on Z. Is it clear? Right? We have applied whatever we know. Just we are writing for this problem, whatever is needed. That's all. Okay, let us go to the next question. Determine whether each of the following relations are reflexive, symmetric, and transitive. That is what we should check for. Now, a relation R is defined on A, which is from 1, 2, 3, so on up till 14. R is a relation, and the condition is also given. Okay. So now we have to check for, is it reflexive, symmetric, or transitive or not. So see, basically till now, means the previous question that we have discussed, here we have an infinite set. So our R, if you are starting to write R is equal to in roster form, okay, if you are writing in roster form all the ordered pairs, then you will never complete because there are infinitely many integers. So that will not work. But here it will work, because here there are less number of ordered pairs, because 1 to 14, that's it. So you can write the relation and check ordered pair by ordered pair. You need not write like A comma A belongs to R, that type of theoretical format. Here it is, means you don't have any other way. This you have to do like this only, because there are infinitely many ordered pairs which will be there. Okay, fine. So here you can do it like this also. So R is equal to, you can write in roster form. What is this saying? Y is equal to 3x. So if y is equal to 3x, what can x take? X can take only those values which are coming from set A. So therefore, if x is 1, y should be equal to 3. If x is 2, y should be equal to 6. If x is 3, y should be equal to 9. If x is 4, y should be equal to 12. If x is equal to 5, then y will be equal to 15. Obviously, see, just before we have discussed, x should come from set A, right? Now, where will y come from? Y also should come from set A only. So therefore, if you take x is equal to 5, then y will be 15. So this mapping is not possible because 15 is not there in our set, right? So you cannot take x is equal to 6 and all of them, because for x is equal to 6, y will be 18. That is not there in set A. So obviously this ordered pair, x should come from set A, y also should come from set A. So that's it. So these are the only possible ordered pairs. Now, is it reflexive? Just by seeing, I can say this is not reflexive because 1, 1 is not there, 2, 2 is not there, 14, 14, none of them are there. But for reflexive, all of them should be there. Okay. So here none of them is there. So just to disprove, you have to give an example. That's all. 1, 1 does not belong to R. implies R is not a reflexive relation. R is not a reflexive relation on A. That's it. Simple. Okay. Next, is it symmetric? It is not symmetric. Why? Because you take one ordered pair 1, 3. 3, 1, is it there? No. So therefore, you got a cross mark. So therefore, this is not symmetric. So 1, 3. 1, 3. Okay. So 1, 3 belongs to R. But 3, 1 does not belong to R. 3, 1 does not belong to R. Implies R is not symmetric. Even if you show one example, that is sufficient. Symmetric relation on A. On A. So we have shown that means we have to decide if it is reflexive, symmetric, transitive or not. So we have done with the other ones. Now means reflexive and symmetric is done. Let us write this one. So if x is 1, y should be equal to 3, 2, 6 and 3, 9, 4, 12. Okay. So now we are checking for transitive. So take this ordered pair. Is there any ordered pair starting with 3? Yes. Okay, fine. So 1, 9 is there. Sorry, 1, 9 should be there. Is it there? No. So therefore, this is not transitive. So 1, 3 belongs to our relation and 3, 9 belongs to our relation. But 1, 9 does not belong to our relation, implies R is not a transitive relation. Not a transitive relation on set A. So very simple. See, here you can do it directly. Means you can write the relation in this form and then you can do the checking. Okay. Let us go to the next question, and that is, let R in the set of natural numbers of set n of natural numbers defined as R is equal to x comma y, where y is equal to x plus 5 and x is less than 4. So is it the same thing, the same question, reflexive or not, symmetric or not, transitive or not? Okay. So though it is defined on set of natural numbers, see here x should be less than 4. X cannot be more than 4. So therefore x can be either 1 or 2 or 3, because x has to be natural number. Of course y also should be natural number, but x should be natural number and x is less than 4, means x can be 1, 2 or 3. So therefore here also writing the relation is very easy. So if x is equal to 1, y is 6. If x is 2, here we have 7, and if x is 3, y is 8. So this is our relation. Now checking for reflexive, symmetric and transitive is very easy. So is it reflexive? No. Why? Because every element of natural number should be mapped to the same element. 1, 1, 2, 2, 3, 3, so on like that. Whichever natural number you take, infinitely many natural numbers are there, and every natural number should be mapped to the same natural number. Here, not even 1 is there. So therefore, this is not, therefore, R is not reflexive. Give one example, that is sufficient. Okay, reflexive relation on natural numbers. Next, 1, 6, you have taken the ordered pair. Reverse, is it there? No. So therefore, 1, 6 belongs to R, but 6, 1 does not belong to R, implies R is not a symmetric relation. Symmetric relation. Okay, and from here on set of natural numbers. Next, go ordered pair by ordered pair. Is there any ordered pair starting with 6? No. So tick mark on 1, 6. Okay. Next, is there any ordered pair starting with 7? No. So therefore, no checking is needed for 2, 7 also. No checking is needed for 3, 8 also. So therefore, this will be a transitive relation because you got tick marks on all of the ordered pairs. So that's all. So that is what you need to write. That is if a1 comma a2 belongs to R and a2 comma a3 belongs to R, then a1 comma a3 belongs to R, rule is never denied by relation R. Therefore, R is transitive relation. On set of natural numbers. R is transitive relation on set of natural numbers. Simple, right? Okay. So this question is also completed. Let us go to the next one. R is a relation which is defined on set A and Y is divisible by X. Okay. So if Y should be divisible by X, means when you divide Y by X, you should get an integer. Okay, fine. So in this one, you can do the other way also, because you know this roster way of writing, it will take little more time, and directly if you do means the normal method, X comma X should belong to R. Okay, this type it will be faster. Here it was small, but here it will be little big. Okay, so that you can realize right away, because if you are taking X is equal to 1, then whatever is the Y, you will get integer only. Means Y can be 1, 2, 3, 4, 5, 6 itself. So therefore 2, so on like this, 1 comma 6. If you take 2, then Y cannot be 1, right? Because 1 by 2 is not an integer. So Y can be 2, Y can be 4, Y can be 6. So with 3 it will be 3 comma 3, 3 comma 6. With 4 it will be 4 comma 4 and 5 comma 5 and 6 comma 6, isn't it? You take 4 on the in Y, you cannot have anything, means 1, 2, 3 is not possible, 4 is possible, 5 and 6 also not possible. So you know it will take some time, otherwise the other one will be even quicker. X comma X belongs to R implies X by X, means this Y is divisible by X, means this X should be divisible by this X. So X by X is equal to 1. So therefore X is divisible by X. X is divisible by X. Divisible. If X is divisible by X, therefore X comma X belongs to our relation. Next, if X comma Y belongs to our relation, can I say Y comma X belongs to our relation? This we can never say, because if X is dividing Y, how can you say Y also divides X all the time? Not possible. If you are saying, let us say for example, 1 divides 2. 1 divides 2. So therefore 1 comma 2 will be there in our relation. But 2 comma 1 will not be there, right? So therefore this will not be symmetric. So if we can write it here, if Y is divisible by X, that does not mean X is divisible by Y. So therefore this is not symmetric. And transitive also, same procedure. Means if X is divisible by Y, okay, something like if X is divisible by Y, Y is divisible, if Y is divisible by X, so 1 divides 2, 2 divides, okay, let us take some other example. So let us say for example, this is 3 and this is 6 and this is 6 and this is 24. So here we will have, means if this number is divisible by this number, means if Y divides X, then I can write Y is equal to some integer into X, and if Z is equal to, Y comma Z, if this also belongs to R, then Z is equal to some integer times Y. So from here, can I say Z is some integer times X? Yes. How? Like this. You put this Y here. So therefore Z is equal to K2 into K1X. So therefore Z is equal to some integer times X, means X divides Z, means X comma Z will belong to our relation, means this is a transitive relation. So this is a general way of writing. Okay, here we have taken Y divides X. So therefore Y is equal to K1X. Next, Z divides Y. So therefore Z is equal to K2 into Y. These two are belonging to our relation. From here, from these two equations, can I say z is equal to some integer times x? Yes. So how do you do it? From these two equations, I want z is equal to some integer times x. I don't want y. So remove y. So therefore, whatever is this y here, you put it here. So therefore, you will have z and x relation. So therefore, this is transitive. So that is, easier. But for transitive, checking here will be, too difficult. Okay, you will see in just a moment. Now you'll see. Is this reflexive? Yes. 1, 1 is there, 2, 2 is there, 3, 3 is there, 4, 4 is there, 5, 5 is there, 6, 6 is there. It is reflexive. Done. Next, is it symmetric? From there, we have seen it is not symmetric. From here also you can see. 1, 1 is there, reverse 1, 1 is there, put a tick mark. 1, 2 is there, 2, 1 is not there, so cross mark. So therefore, this is not symmetric. Why? Because 1, 2 is there, 2, 1 is not there. Next, is it transitive? So you have to check, ordered pair by ordered pair, and it will take some time. 1, 5. Okay. Is there any other ordered pair starting with 1? Yes. So many are there. So 1, 2 is there, 1, 3 is there, 1, 4 is there, 1, 5 is there, 1, 6 is there. So therefore, put a tick mark. So if you check like that, you will get tick marks on all of them. So therefore, this will be transitive. Okay. So in this problem, this method will be quicker. Okay. So let us go to the next question. Okay. So next we will take equivalence classes and partitions. So let us start the next topic.